Right now, 11 billion miles from where you are sitting, a spacecraft is moving through material that no model correctly predicted. Not close to predicted, 40 times off. Voyager 1 crossed the boundary of our solar system on August 25, 2012, and the plasma on the other side was 40 times denser than 50 years of careful physics had described. One instrument registered the anomaly so sharply that the first assumption was instrument failure. It was not instrument failure. The plasma wave instrument, running on roughly 4 watts of power, oscillating in a medium no human device had ever touched, was reporting exactly what was there. Voyager had not malfunctioned. The models had. The signal confirming this took 22 hours and 35 minutes to reach Earth. By the time it arrived, the crossing had already happened. Not recently. 8 months earlier. The first human-made object in interstellar space had been there for most of a year before anyone could confirm it. If you have ever wondered what it looks like when science discovers it was wrong about something right outside the front door, this is that story. If spending quiet time at the edge of the known is your kind of evening, a subscribe helps this channel find more people like you. Now, let us begin. The sun does not end. It dissolves, and the place where it dissolves is nothing like the line on the diagram. Every diagram of the solar system you have ever seen is lying to you by omission, not about the planets, about what comes after them. The diagram shows Neptune at the edge and then white space. That white space represents a decision the illustrator made. It does not represent what is actually there. What is actually there is an envelope, a bubble, a region of space carved out by the sun's own breath, extending far beyond Neptune, far beyond Entine, far beyond any planet, out to a boundary roughly 120 times the Earth-Sun distance. The bubble has a name. It is called the heliosphere. The sun does not stop radiating light. It also does not stop radiating matter. Continuously, without pause, the sun sheds particles from its outermost atmosphere. Electrons and protons accelerated outward at between 250 and 750 kilometers per second, streaming in every direction. This is the solar wind. It has been blowing for 4.6 billion years without interruption. Every second, the sun loses roughly 1 million tons of mass to this outflow. The loss is negligible against the sun's total mass. The reach of it is not. The solar wind travels outward and thins as it expands across an ever larger sphere. It does not thin to nothing. It travels until it collides with resistance. That resistance is the interstellar medium, the gas and dust and magnetic field lines that fill the space between stars. The two pressures meet. They push against each other. At the point where they balance exactly, the solar wind stops. That point is the heliopause. The heliopause is not a wall, it is a pressure balance. On one side, solar wind particles. On the other, interstellar plasma. The boundary holds because the forces are equal. Move past it in any direction and you are no longer inside the sun's physical influence. You are in a different medium entirely, interstellar space. Before the heliopause, you cross 2 other structures. The termination shock at roughly 85 astronomical units, where the solar wind drops from supersonic to subsonic speeds, slowing suddenly the way a river slows when it hits a wide, shallow pool. Then the heliosheath, the turbulent region where the slowed wind piles up against the outer boundary, thick and chaotic, extending another 30 to 40 AU. Then the heliopause itself, at approximately 121 AU, in the direction Voyager 1 was traveling. 1 astronomical unit is 93 million miles, the Earth-Sun distance. The heliopause is 121 of those. That is 1121 of those. That is 2 billion miles from the sun. Drive a car at highway speed, without stopping, toward the heliopause. You will arrive in approximately 21,000 years. You would start the drive before agriculture existed, before any city on Earth was built. You would still be driving now. Light covers the same distance in 17 hours. The signal Voyager 1 sends back from the other side of that boundary takes 22 hours and 35 minutes to arrive. We are always listening to yesterday. Here is the thing that matters. Scientists had been modeling the heliosphere for 50 years before Voyager crossed the boundary. They had named all the layers. They had placed the termination shock roughly where Voyager found it. They had described the heliosheath. They had predicted the heliopause location to within a few AU. The architecture of the model was correct. The models knew the heliosphere existed. They knew roughly where its edges were. What they had never done was stand on the other side and take a direct measurement. The heliosphere is like a house you have lived in your entire life. You know every room. You have mapped every draft coming through the walls. You have inferred what the street looks like from the sound of traffic outside. But you have never stepped outside and looked back at the building. You do not know what the exterior walls are made of. You do not know how thick they are. You do not know what the neighborhood looks like from the street. Voyager 1 was the first instrument humanity ever sent outside. What it found when it got out there rewrote the exterior of the house. There is something worth being precise about before we go further. The heliosphere is not a physical object. It has no surface in the way a planet has a surface. It is a region defined by a pressure balance, and that region shifts as the conditions on both sides of it change. When the sun is more active, stronger solar wind, the heliosphere expands outward. When solar activity drops, the interstellar medium gains ground. The boundary moves. Over the sun's roughly 11-year activity cycle, the heliopause breathes in and out by perhaps a few AU. Over the 47 years of Voyager's flight, the heliosphere has expanded and contracted multiple times. The crossing point Voyager reached was not a fixed target in space. It was a dynamic balance that had shifted since the mission launched. Every star with a stellar wind has an analogous structure. The Sun's heliosphere is our version of a phenomenon called an astrosphere. For stars moving rapidly through the local interstellar medium, astronomers can sometimes detect a bow shock ahead of the stellar wind, a compressed arc of material where the stellar wind hits the oncoming interstellar gas head-on. The Sun's heliosphere is too large and too close for us to photograph whole from inside it. We cannot step back far enough to see the full structure. The two Voyager probes are the only instruments ever placed outside it, and even they sample one point on the boundary in one direction. They cannot photograph the entire structure. They can only report conditions at their specific location. The word heliosphere was coined by Ludwig Biermann in the 1950s, around the same time that the existence of the solar wind itself was still controversial. Eugene Parker published his theoretical prediction of the solar wind in 1958. The paper was initially rejected by journal reviewers who considered the idea of a continuous particle outflow from the sun implausible. It was eventually published. Within a few years, direct measurements confirmed it. The Soviet Luna 1 spacecraft in 1959 detected the solar wind for the first time. The American Mariner 2 spacecraft confirmed and characterized it in 1962. Before those measurements, the existence of a continuous particle stream from the Sun was genuinely not settled. Pioneer 10 and Pioneer 11 launched in 1972 and 1973 were the first spacecraft to cross the asteroid belt and observe the outer planets from close range. Both were eventually sent on trajectories that would take them out of the solar system in different directions from Voyager. Both went silent before reaching the heliopause. Pioneer 10 lost contact in 2003. Pioneer 11 in 1995. Neither carried instruments capable of the measurements Voyager would make, and neither lasted long enough to reach the boundary. Voyager, with more capable RTGs and a more robust instrument design, survived long enough to reach what Pioneer could not. Here is what 11.2 billion miles means, worked through properly. Raw number, 11T 200,000 T 100,000 miles. Fastest human reference, the New Horizons spacecraft. The fastest launch probe in history at approximately 36,000 miles per hour would take about 35 years to cover that distance. Time-based anchor. In the time it takes a child born today to reach retirement age, a spacecraft moving at the fastest speed a rocket has ever achieved would not yet be at the heliopause. Sensory consequence, light, which crosses from Earth to Moon in 1/13 seconds, takes 22 hours to cross this distance. Emotional meaning, the entire history of human civilization, from the first cities to the present day, fits inside the round-trip communication time to Voyager by a factor of 3. The inference problem runs deeper than it looks. The observations used to build the heliosphere model were made from inside the structure being modelled. The light that passed through the interstellar medium to Earth's telescopes also passed through the heliosphere before reaching the detector. The cosmic rays arriving at Earth's surface had already been filtered by the heliosphere. The model of the external medium was built using data that the heliosphere had already shaped. This circularity is not fatal to the inference, but it introduces a systematic limitation that can only be resolved by stepping outside and measuring directly. The model says, based on what the filtered data shows, the unfiltered medium should look like this. The direct measurement says, the unfiltered medium looks like this. When those two statements disagree by a factor of 40, the inference had a problem. The circularity prevented it from detecting. The termination shock deserves more than a passing mention. It is not just a boundary on a diagram, it is the first place where something physically dramatic happens to the solar wind. The solar wind travels outward from the Sun at between 250 and 750 kilometers per second, which puts it firmly in the supersonic category. At those speeds, the wind cannot simply decelerate smoothly when it meets the resistance of the interstellar medium. Supersonic flows do not slow gradually. They shock abruptly in a narrow region where the velocity drops and the density and temperature spike. Think of the condensation shock that forms on a fighter aircraft as it approaches the speed of sound, the visible pressure wave that appears at specific points on the airframe, or think of the standing wave in a fast river, where the water hits a wide, shallow section and suddenly backs up and churns. The termination shock is the solar wind's equivalent of that standing wave, sitting at roughly 85 to 94 AS/UL depending on solar activity and direction. Voyager 1 crossed it in December 2004, 27 years of flight to reach the first shock. The heliosheath, the region between the termination shock and the heliopause, is not calm. The solar wind that passed through the termination shock is now subsonic, slowed and heated, and it piles up against the outer boundary like backed-up water behind a dam. The flow in the heliosheath is turbulent, compressed and deflected, the original outward directionality of the solar wind largely lost in the complex mixing of the region. The heliosheath is also not uniform in thickness. The nose of the heliosphere, facing into the direction of the Sun's motion through the interstellar medium, has a thinner heliosheath because the external pressure is highest there and the boundary is closer. The tail stretches behind, much thicker, the slowed solar wind piling up in the wake. Voyager 1 travelled through roughly 37 AS/UU of heliosheath material between the termination shock crossing in 2004 and the heliopause crossing in 2012. That transit took 8 years. For comparison, the entire distance from the Sun to the termination shock took 27 years. 8 years for 37 AU. The heliosheath is proportionally thick. The solar system is moving through the local interstellar medium at roughly 17 miles per second relative to the surrounding gas. This is not the orbital speed of the Earth or the solar system's speed relative to the galactic center. It is the speed of the Sun relative to the gas and dust in our immediate neighborhood. This motion has a direction. The Sun is moving roughly toward the constellation Ophiuchus in the direction of a point in space called the solar apex. The opposite direction, where the solar system is coming from, is called the solar antipex. The heliosphere is moving through the interstellar medium nose first toward the solar apex. The nose is compressed. The tail, the region behind the Sun in the antipex direction, extends far beyond the nose. Voyager 1 crossed the heliopause near the nose direction. Voyager 2, which took a different trajectory, inclined toward the solar equatorial plane, crossed on the flank, closer to the equatorial direction than the nose. Both crossings were on the compressed, leading side of the heliosphere. The solar wind varies. It is not a constant output. The Sun goes through an approximately 11-year activity cycle during which the solar wind's speed, density, and magnetic structure change significantly. At solar maximum, the wind is stronger and more variable, carrying more magnetic complexity. At solar minimum, it is smoother and somewhat less dense. The heliosphere responds to these variations. It breathes with the Sun. The termination shock location has been observed to move inward and outward by several AU over activity cycle timescales. The heliopause presumably responds similarly, though with some delay, as the pressure changes propagate outward. Voyager 1 crossed the heliopause in 2012, which was approaching solar maximum of solar cycle 24. The crossing point and conditions were set by the specific solar activity state at that time, not by some average condition. The numbers for the heliosphere structure deserve to be walked through once in a format that makes them feel real rather than abstract. Start at the Sun. Move outward at the speed of the solar wind, roughly 450 kilometers per second on average. It takes the solar wind approximately 3 to 4 days to reach Earth at 1 AU, another 3 to 4 months to reach Jupiter at 5 AU, almost a year to reach Saturn at 9.5 AU, 2 years to reach Uranus at 19 AU, 3 years to reach Neptune at 30 AU. Now keep going. The wind continues outward, thinning as it spreads, carrying the Sun's magnetic field in an ever larger spiral, for another 55 to 64 AU beyond Neptune before it hits the termination shock. That is another 5 to 6 years of travel time for the solar wind, and then 30 to 40 more AU of turbulent heliosheath, another 3 to 4 years of wind travel time at the slowed post-shock speed before the heliopause at 120 AU. The solar wind that crossed the heliopause as Voyager 1 was crossing it had left the Sun approximately 10 years earlier. It had been travelling for a decade before it ran out of solar system. The heliosphere is also not sitting still in the galaxy. The entire structure, Sun plus heliosphere plus all the planets, is orbiting the centre of the Milky Way at roughly 220 kilometers per second. This orbital speed dwarfs the solar wind speed and the speed of any spacecraft humanity has launched. In the time it takes to read this paragraph, the entire solar system has moved approximately 1,300 kilometers through the galaxy. In the 47 years since Voyager launched, the solar system has moved roughly 330 billion kilometers along its galactic orbit. Voyager itself has moved roughly 25 billion kilometers relative to the Sun. Relative to the galactic center, Voyager is somewhere it has never been before and will never be again. Every measurement it takes is a measurement from a unique point in space that no human instrument has occupied before or will occupy after. It took Voyager 35 years to reach a boundary that light crosses in 17 hours. 35 years. 17 hours. Same distance. One covers it before breakfast. The other took longer than most careers last. This is not a failure of engineering. This is the nature of the distance. And this is still inside our own solar system's outermost envelope. The nearest star, Proxima Centauri, is 424 light-years away. 1 light-year is about 8,760 light-hours. The heliopause is approximately 17 light-hours from the Sun. Expressed as a fraction of the gap to the nearest star, the distance Voyager crossed is less than 1/1,000. Not 1/5, not 1/50th. 1/1,000th. We have not left the neighborhood. We have stepped off the porch. Voyager 1 launched September 5, 1977. Its primary mission was Jupiter and Saturn. Nobody in 1977 planned for the heliopause. They planned for Jupiter in 1979 and Saturn in 1980. And then whatever happened after. What happened after was that the spacecraft kept working for 47 years. Without a single in-person repair. The Jupiter flyby was the key that unlocked everything. Jupiter's gravity bent the trajectory and accelerated the spacecraft, a gravity assist that cost Jupiter a velocity change so small no instrument could measure it, and gave Voyager enough speed to matter over decades. After Saturn, the probe was aimed above the plane of the solar system and released. No more planets. Just outward. Consider what 38,000 miles per hour means. The fastest military aircraft ever flown, the SR-71 Blackbird, reaches about 2,193 miles per hour. Voyager travels 17 times faster than that. The Apollo command module hit approximately 25,000 miles per hour during re-entry, the fastest any human has ever traveled. Voyager beats that by 50%. At 38,000 miles per hour, crossing 11 billion miles per hour, crossing 11 billion miles still takes 35 years. the spacecraft is powered by 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity through solid-state thermoelectric converters. No moving parts, no fuel to burn, no solar panels, which would be useless this far from the sun. Just the slow warmth of a radioactive element decaying at a rate physics set for 6 billion years ago, when the plutonium was forged inside a dying star. At launch, the RTGs produced about 470 watts. Plutonium-238 has a half-life of 87 years. 7 years. After 47 years, the remaining output is roughly 230 watts. At 230 watts covers every function on the spacecraft. The attitude control thrusters, the heaters keeping electronics from freezing near absolute zero, the 23-watt radio transmitter broadcasting back to Earth. After all of that, the science instruments share approximately 4 watts. 4 watts. The power draw of a small nightlight. The science payload measuring interstellar space for the first time in history runs on the power of a nightlight. The signal that the 23-watt transmitter produces is almost incomprehensible by the time it reaches Earth. Spread across a sphere 22 light hours in radius, the power arriving at the 70-meter dish at Goldstone, California is roughly 1/10 billionth of a watt. That dish, the largest in NASA's deep space network, captures Voyager's signal at barely detectable strength. The data rate is approximately 160 bits per second. Every measurement takes time to encode, time to transmit, and then 22 hours to travel. In 2023, a memory chip in the flight data system became corrupted. The spacecraft began sending garbled data. Engineers at JPL diagnosed the problem remotely, working with software written in the 1970s for hardware no longer manufactured, communicating through a 22-hour one-way delay. Each diagnostic command took 22 hours to arrive. Each response took 22 hours to return. A single exchange took 44 hours. The repair took months of iterative steps. They relocated the affected software code to undamaged memory regions. It worked. Voyager resumed normal operations. There is no second spacecraft standing by. There is no repair mission. There is the probe, the signal, the 22-hour delay, and the physics. That is all there is. And it has been enough. By 2012, when the heliopause crossing occurred, only 4 science instruments were still operating. The magnetometer, the low-energy charge particle instrument, the cosmic ray subsystem, and the plasma wave science instrument. The plasma science instrument, which would have directly measured plasma density and velocity, failed in 1980 during the Saturn encounter. This loss meant the definitive measurement at the heliopause would have to be inferred, not directly taken. The detection of the crossing unfolded slowly. Multiple candidate crossings had been identified in 2011 and 2012 and then rejected when the data did not fully confirm them. In the summer of 2012, particle fluxes and magnetic field readings both shifted dramatically. Some team members believed the crossing had occurred, others were not certain. Without a direct plasma measurement, the evidence remained ambiguous. The confirmation came from physics 11 billion miles away. A coronal mass ejection from the Sun in March 2012 sent a fast plasma wave outward through the solar system. The wave traveled for months, moving faster than the ambient solar wind, and reached Voyager 1 in October 2012. When it hit the surrounding plasma, it drove oscillations. The plasma wave science instrument detected those oscillations. The frequency of plasma oscillations is set by the electron density of the medium. Calculate the frequency. Calculate the density. The density was 0.08 electrons per cubic centimeter. Don Gurnett at the University of Iowa, principal investigator for the plasma wave instrument since 1977, understood immediately. Inside the heliosphere, density runs around 0.02 electrons per cubic centimeter. The predicted interstellar value was similar. The measured value was 40 times higher. The paper was published in Science on April 9, 2013. The crossing had occurred approximately 12 months earlier. When the announcement was made, Voyager 1 had already been in interstellar space for 8 months. The 22-hour signal had been delivering data from interstellar space for almost a year before anyone was certain what they were hearing. The planetary alignment Gary Flandreau identified in the mid-1960s was the result of a geometry that recurs roughly every 176 years. The outer planets were arranged such that a spacecraft could use each planet's gravity in sequence to redirect and accelerate toward the next one, without carrying propellant for each leg, Jupiter to Saturn to Uranus to Neptune, each world's gravity bending the trajectory toward the next, each flyby adding or redirecting velocity. Flandreau was a graduate student at JPL performing routine orbital calculations when he identified the window. The window would close in the early 1980s. If NASA waited, the next opportunity would be in the 2450s. The Voyager program was, in significant part, a response to a calendar. At Jupiter in March 1979, Voyager 1 returned images that forced revision of planetary science in real time. Io, the innermost of Jupiter's large moons, was expected to be an ancient cratered surface. What Voyager found was active volcanoes. Io was being continuously resurfaced by eruptions driven by tidal heating from Jupiter's gravitational flexing. The prediction of tidal heating by Stanton Peele and colleagues was published in the same issue of Science as the Voyager images confirming it in March 1979. The prediction arrived in print at almost the same moment as the observation. At Saturn in November 1980, Voyager 1 passed closely by Titan, Saturn's largest moon, and characterized the dense nitrogen atmosphere that had been inferred but never directly sampled. The Titan geometry was the one that sent Voyager 1 upward out of the ecliptic and away from any further planetary targets. The mission that discovered Io's volcanoes ended at Saturn and became something else entirely. The physics of the RTG power decline is simple and inescapable. Plutonium-238 decays by emitting alpha particles. The rate of decay, and therefore the heat output, decreases exponentially according to the half-life of 87. 7 years. After one half-life, output halves. After 47 years, which is roughly 0.54 half-lives, the output has declined to approximately 69% of the original. But the thermoelectric converters themselves also degrade. The temperature difference they exploit decreases as the hot side temperature drops with declining plutonium output, and conversion efficiency decreases. The combined effect means the electrical output after 47 years is roughly 50% of the original 470 watts, or about 230 watts. This decline is predictable. It is not a failure. It is physics working exactly as designed. The problem is that 230 watts minus all the housekeeping functions leaves 4 watts for science, and 4 watts is enough for a handful of instruments but not the full payload. The 70-meter dish at Goldstone, California has been receiving Voyager signals since 1977. It is aimed at a specific patch of sky for hours during each tracking session. Voyager 1 transmits at 23 watts in the X-band frequency range, roughly 8 GHz. By the time that signal has spread across a sphere 22 light-hours in radius, the power flux at Earth's surface is approximately 10 to the power of minus 20 watts per square meter. The dish collects this over its collecting area of roughly 4,000 square meters. The received power is on the order of 10 to the minus 16 watts. This is far below the noise floor of ordinary electronics. Detecting it requires the dish's extremely low noise receiver systems, which operate cooled close to absolute zero to minimize thermal noise. The signal processing required to extract meaningful data from this level of power represents decades of accumulated engineering refinement. The Voyager Extended Mission, the Voyager Interstellar Mission phase that began in 1989 and continues today, costs approximately $5 million per year, divided across 2 spacecraft. The total cost of the extended mission through 2024, roughly 35 years of operations, is approximately $175 million. For that investment, humanity received the first direct measurements of the interstellar medium in our immediate vicinity, confirmation that the heliosphere boundary is sharper than any model predicted, the first detection of a plasma density outside the heliopause, and the discovery of a 40 times discrepancy that is now reshaping heliospheric physics. No other mission in the history of space science has returned data of this uniqueness per dollar spent. The The cost of the entire extended mission is less than the cost of a modest Earth-observing satellite. The 2023 Flight Data System anomaly is worth understanding in detail for what it reveals about the nature of this kind of science. The FDS contains approximately 70 kilobytes of memory in total. This is not a rounding error. This is the actual memory of the computer managing interstellar science operations for humanity's only interstellar probe. In November 2023, one small section of this memory became corrupted, apparently due to decades of accumulated radiation damage from cosmic rays. The FDS began reading instructions from the corrupted location and transmitting the results, which were garbled. Engineers received the garbled telemetry 22 hours after it was generated. They spent weeks analyzing it before identifying the source. The repair required writing new software instructions to route the FDS around the corrupted memory block and relocate the affected code to good memory. Each attempt was sent to the spacecraft took 22 hours to arrive, executed, and the results took 22 hours to return. A full diagnostic and response cycle took 44 hours. The repair was completed in April 2024. Voyager 1 resumed normal science operations. The engineering team that accomplished this repair was working with documentation from the 1970s on hardware no longer manufactured across a communication link that makes real-time troubleshooting physically impossible. The signal physics deserve one more level of detail to make the scale of the communication challenge concrete. Voyager's transmitter broadcasts at 23 watts in the X-band frequency range, approximately 8-band frequency range, approximately 84 GHz. The signal spreads outward in all directions from the spacecraft's high-gain antenna, though the antenna is shaped to concentrate the beam in the direction of Earth. By the time the signal has traveled 22 light hours, it has spread across a sphere whose surface area is approximately 5 × 10 to the power of 30 square meters. The total transmitted power of 23 watts is distributed across this sphere. The receiving antenna at Goldstone has an effective collecting area of roughly 4,000 square meters. The fraction of the transmitted power that the antenna intercepts is approximately 4,000 divided by 5 × 10 to the 30, or about 8 × 10 to the minus 28. Multiply this by 23 watts and you get roughly 2 × 10 to the minus 26 watts received. This number is so small that it requires special notation to write and special engineering to detect. The noise floor of room temperature electronics is approximately 10 to the minus 20 watts. The signal is 6 orders of magnitude below this threshold. Detecting it requires cooling the receiver to near absolute zero to reduce thermal noise, amplifying with the lowest noise amplifiers available, and processing the signal with filtering techniques refined over decades of deep space communication. The management of a spacecraft at 22-hour signal delay requires a specific kind of operational philosophy that has no direct parallel in other engineering contexts. You cannot respond to events, you can only prepare for them. Every command sent to Voyager is a commitment to a course of action that cannot be reversed for 44 hours. If the command has an error, or if conditions on the spacecraft have changed by the time the command arrives, the spacecraft will execute the command anyway, because there is no way to stop it. This requires the operations team to think through the implications of every command before sending it to build in contingencies that the spacecraft can execute autonomously if conditions deviate from expectations, and to trust the autonomous systems to handle anything that happens between the command being sent and the response being received. The result is a mission operations style that is deliberate, conservative, and deeply dependent on the quality of the original engineering. Spacecraft designed to operate autonomously in uncertain conditions for extended periods. The Voyager design has been adequate to this requirement for 47 years. The team managing Voyager today is small, a handful of engineers and scientists at JPL, several of whom have worked on the mission for decades, managed the day-to-day operations of both spacecraft. The institutional knowledge accumulated over 47 years exists partly in written documentation and partly in the minds of people who have worked with the spacecraft long enough to understand its specific quirks. When those people retire, that knowledge has to be transferred. JPL has been managing this knowledge transfer for years, bringing younger engineers into the mission and pairing them with long-tenured team members to document and pass on what the formal documentation does not capture. This is one of the less discussed challenges of a long-duration mission. The spacecraft design is fixed. The team managing it is not. Over 47 years, the people who built it, launched it, and operated it through the planetary encounters are mostly gone. The mission continues. The knowledge of how it actually works at the level of detail that matters in an emergency is a fragile thing. The 22-hour signal delay creates a specific relationship between the science team and the data they receive. When a measurement arrives from Voyager, it describes conditions as they were 22 hours earlier. By the time the team analyzes the data, runs models, and decides on the response, another day may have passed. The command implementing that response takes 22 hours to arrive. The earliest the spacecraft can respond to something observed in the data is more than 2 days after the observation. For slowly changing phenomena, like the gradual evolution of plasma properties in the outer heliosphere, this delay is manageable. The science team plans observations months in advance, designs instrument operation schedules that accommodate the delay, and manages the mission on week-to-month timescales rather than minute-to-hour timescales. The anomaly events like the 2023 FDS failure test this system because they require timely diagnosis and response. The 2023 repair took months not because the diagnosis was slow, but because each diagnostic step required a 44-hour round trip, and multiple steps were needed. The Voyager mission budget in its extended phase deserves a specific comparison that makes the value concrete. A single Tomahawk cruise missile costs approximately $1.5 to $2 million. The annual operating budget of the Voyager interstellar mission is roughly $5 million per year. For the cost of 2 to 3 cruise missiles per year, humanity maintains the only direct measurement capability in interstellar space. The cost per scientific data point, measured in terms of uniqueness, is lower for Voyager than for any other science mission in history. The data it returns from beyond the heliopause cannot be obtained any other way. Not by telescope, not by theoretical calculation, not by any instrument that has not physically crossed the boundary. Voyager is not the only way to do heliospheric science. It is the only way to do interstellar science with instruments that have already made the crossing. The 160 bit per second data rate from Voyager is worth sitting with for a moment. Modern internet connections transfer data at hundreds of millions of bits per second. Voyager transmits at 160. In 1 second, a modern connection could transfer a high-resolution photograph. In 1 second, Voyager transmits about 20 characters of text. A single hour of Voyager science data, transmitted at 160 bits per second, contains approximately 576,000 bits, or about 72,000 bytes, roughly the size of a short document. That document contains measurements of the plasma density, the magnetic field strength and direction, the cosmic ray flux at multiple energies, and the plasma wave oscillation frequencies at Voyager's current position in interstellar space. None of these measurements exist anywhere else. No other instrument has ever made them at this location. A 72 kilobyte document arriving every hour from interstellar space at the cost of 4 watts of power and 22 hours of signal travel time, representing the entirety of humanity's direct knowledge of the medium between our solar system and the stars. The models were not slightly off. They were wrong by a factor that does not happen in mature science. A scientific model is not a guess. It is a prediction constrained by every available observation, built with decades of work, tested repeatedly, revised when it fails smaller tests, trusted when it passes them. The model that existed for the heliosphere boundary before Voyager 1 crossed had real, verifiable successes. It placed the termination shock at roughly the right distance. It correctly predicted the existence of the heliosheath. It described the behavior of cosmic rays in the outer heliosphere in ways that matched measurements from inside. These predictions came true. The model was not careless work. The consensus prediction for the electron density of the local interstellar medium just outside the heliopause was approximately 0.2 electrons per cubic centimeter. The measurement was 0.08, 40 times, not 40% high. 40 times higher, 40% high. If you built a structural beam designed to hold 10,000 pounds and it held 400,000 without failing, you would not call that a calibration adjustment. You would call it a description of a different physical reality. The first place to look for an explanation is the instrument. This is not defensiveness. It is correct scientific procedure. The plasma wave instrument had been in space for 35 years when it made the measurement. 35 years of radiation exposure, thermal cycling, component aging. The team went through the calibration history. They checked the noise floor. They looked for drift signatures and known failure modes. Nothing. The instrument was performing correctly for its age and history. No known degradation mode produces a factor 40 error in the density calculation. The measurement was real. The second explanation was local variation. The interstellar medium is not perfectly uniform. If Voyager had crossed through a density enhancement, a clump of denser material at the specific crossing point, the reading might be locally accurate but unrepresentative of the surrounding medium. Under this interpretation, the models were right on average, and Voyager hit an unlucky dense pocket. This explanation has a testable prediction. If the reading reflects a local clump, it should resolve. As Voyager moves deeper into the interstellar medium, away from the crossing point, the density should drop back toward the predicted background. It did not drop. Over the months and years following the crossing, as Voyager traveled further from the heliopause, the density remained elevated, not at exactly zero Ts every measurement, because the medium genuinely varies, but consistently far above 0 Ts. 0 Ts, no return to baseline, no resolution. The density was not a spike at the crossing, it was the floor of the medium Voyager had entered. Local clump, eliminated. The third explanation was geometric. The heliosphere is not a perfect sphere. The nose, the leading edge in the sun's direction of travel, is more compressed than the tail. If the nose compression is significantly greater than modelled, Voyager's crossing point might systematically sample denser Nebulae matter than the average. Revise the geometry, and perhaps the density resolves. This argument has genuine physical merit. The nose compression is real, and the models may have underestimated it. But this rung of the ladder has a specific problem. The density is not the only anomaly. 3 instruments, 3 physical phenomena, all 3 wrong. The magnetometer showed a magnetic field transition at the heliopause that was sharper than any model had described. Inside the heliosphere, the solar magnetic field dominates, wound into the Parker spiral by the combination of solar wind outflow and solar rotation. Outside, the interstellar magnetic field takes over, pointing in a different direction set by the galactic magnetic environment. This direction change was expected. What was not expected was how abrupt it was. The models predicted a mixing zone, a gradual handoff across some finite distance. The magnetometer found a wall, a hard edge where the field direction changed over a region far smaller than any model had described. The cosmic ray subsystem showed the same character from a different angle. Galactic cosmic rays, high-energy particles produced by supernovae and other energetic events throughout the galaxy, are partially filtered by the heliospheric magnetic field. Inside the termination shock, their flux is suppressed. Moving outward through the heliosheath, the flux should increase gradually. At the heliopause, the models predicted a continued gradual increase leveling off at the interstellar background. What Voyager measured was a step function. The galactic cosmic ray flux jumped sharply at the heliopause. The anomalous cosmic rays, particles accelerated within the heliosphere itself, dropped sharply. Not a gradual transition. A step. The boundary filtered cosmic rays far more abruptly than any model had described. Plasma density 40 times the predicted value. Magnetic field boundary, sharper than modelled. Cosmic ray transition, step function not gradient. 3 instruments, 3 independent physical quantities, 3 independent departures from the model in the same direction. A local density clump cannot simultaneously make the magnetic boundary sharper and the cosmic ray transition more abrupt. These phenomena do not co-vary in ways that a single localized anomaly would produce. They are measuring different aspects of the same physical reality, and all 3 of them are saying the same thing. The heliopause is a harder, sharper, more definite boundary than 50 years of modelling had described, and the material on the other side of it is denser than any model predicted. Before we continue further, if tonight is landing the way we hoped, a like or subscribe helps this channel reach more people who need exactly this kind of quiet. The most coherent partial explanation involves the specific structure of the local interstellar environment. The solar system is currently embedded in the local interstellar cloud, a region of partially ionized gas roughly 30 light-years across with properties distinct from the surrounding medium. The local interstellar cloud is itself inside the local bubble, a cavity in the galactic gas roughly 1,000 light-years across, excavated by a series of supernova explosions millions of years ago. The boundary of the local bubble is denser than its interior because the expelled gas piled up at the edges. The specific region of the local interstellar cloud immediately outside our heliopause may genuinely be denser than the large-scale averages the models used. The models were built from indirect observations of the cloud as a whole. The cloud has internal structure. Voyager may have crossed into a denser region than the average the models described. This explains some of the density. It does not explain the sharpness of the magnetic boundary or the step function character of the cosmic ray transition. Those anomalies require separate explanations, and those explanations are still being worked out. The data defines the problem. The community has not yet agreed on the solution. What is not debated is the core finding. The heliopause behaves more like a membrane than a gradual fade. Sharp, definite, with material 40 times denser on the outside than the inside view predicted. The 22-hour signal still arrives. Every day it delivers measurements from a medium that broke the model used to predict what it would contain. The number 0, SN2 electrons per cubic centimeter, deserves a concrete translation. Air at sea level contains approximately 27 billion molecules per cubic centimeter. The predicted interstellar medium outside the heliopause contains 0.002 electrons per cubic centimeter. That is 2/1000ths of a single electron per cubic centimeter. Not per meter per centimeter. If you filled a standard kitchen with interstellar medium at this density, you would have roughly 1.7 electrons to work with. In any ordinary sense, this is a near-perfect vacuum. The anomaly Voyager found is not that the interstellar medium is dense, it is that the density is 40 times higher than this near-perfect vacuum prediction. In a medium where 0 dot rhyme, 0.02 was the expected value, finding 0. 0.8 is not a refinement. It is a different physical description. The magnetic field anomaly deserves its own careful treatment. At the heliopause, the magnetic field was expected transition from the Parker spiral pattern of the solar wind to the interstellar field orientation over a transition region of some finite width. The width of this mixing zone in the models was described by diffusion physics. Charged particles scatter off magnetic field irregularities, and the typical scattering length sets the scale over which the two magnetic regimes mix. The scattering lengths at the relevant energies are measured in AU. The mixing zone should be measured in AU. The magnetometer found a transition occurring over a distance far smaller than AU, not a gradient across tens of AU, a sharp directional change over a region that might be measured in fractions of an AU. This implies that charged particle diffusion across the boundary is far more suppressed than the models assumed, which in turn implies the magnetic structure of the heliopause is organized in a way the models did not capture. The cosmic ray step function character is the most theoretically puzzling of the three anomalies. Standard cosmic ray physics predicts that particles in the energy range Voyager's cosmic ray subsystem measures should have mean free paths, average distances between scattering events of many AU. A mean free path of many AU means the transition from heliospheric to interstellar cosmic ray conditions should be spread over many AU. The Voyager data shows a transition over a distance much smaller than the mean free path predictions. Either the mean free path calculation is wrong for these conditions, or something about the heliopause geometry is confining cosmic rays on the outside more effectively than diffusion physics describes. Or the interstellar magnetic field just outside the heliopause has a specific orientation that creates a kind of magnetic mirror that reflects cosmic rays. None of these candidates is fully confirmed. The anomaly is real. The explanation is still being worked out. The local interstellar cloud has been studied through ultraviolet absorption features in the spectra of nearby stars. When starlight passes through the cloud before reaching Earth, it picks up absorption signatures at specific wavelengths corresponding to hydrogen, helium, oxygen, carbon, and other elements in the cloud. These absorption features have been mapped across nearby stars and used to infer the cloud's extent, composition, and rough density. The inferred density from these observations is approximately 0.1 hydrogen atoms per cubic centimeter, or a somewhat lower electron density because the hydrogen is partially ionized. The Voyager electron density measurement of 0.08 is consistent with being inside a denser region of this cloud rather than the average. The cloud has internal structure. The stellar absorption measurements cannot resolve because they average over the entire path length from star to Earth. Voyager's in situ measurement samples the specific local density at the crossing point, not an average. If the density of 0.0 electrons per cubic centimeter is representative of the medium surrounding our heliosphere in all directions, the implications compound. The external pressure on the heliosphere would be 40 times what the standard models assumed. The heliopause location, which depends on the balance of solar wind pressure against external pressure, would be at a different distance in the standard models than it actually is. The heliosphere would be smaller. The termination shock would be closer to the Sun. The heliosheath would be thinner. The cosmic ray shielding provided by the heliosphere would be reduced relative to model predictions. Each of these is a quantitative change that cascades through every calculation that used the standard model as an input. None of these changes necessarily makes the heliosphere uninhabitable or dramatically different in character, but they are genuine corrections and they compound across everything the standard model was used to calculate. The sharpness of the heliopause boundary is a genuine puzzle in plasma physics, not just an observational curiosity. In a standard magnetohydrodynamic model of the heliopause, the boundary is maintained by the pressure balance between solar wind and interstellar medium, and its thickness is set by the gyroradii of the ions on both sides. The gyroradius is the radius of the circular orbit a charged particle traces around a magnetic field line. In the outer heliosheath plasma, proton gyroradii are on the order of a few AU. A boundary that is sharp compared to proton gyroradii is physically unusual. It implies either that the magnetic field structure at the boundary creates a more effective barrier than the simple gyroradius argument suggests, or that there is a specific physical process maintaining the boundary's sharpness against the diffusive tendency of the ions. Proposed mechanisms include a current sheet at the heliopause interface, magnetic reconnection events that continually re-establish a sharp boundary despite diffusion, and the role of pickup ions, ionized interstellar atoms that have entered the heliosphere, in the pressure balance. None of these proposals has been definitively confirmed as the dominant mechanism. The sharpness is observed. The physics maintaining it is actively debated. The three anomalies together imply that the heliopause behaves less like the gradual transition zones familiar from inner heliospheric physics and more like what physicists would call a tangential discontinuity. A tangential discontinuity is a boundary across which there is no flow, just a sharp change in the properties of the plasma on each side. The velocity, density, temperature, and magnetic field direction can all change sharply across a tangential discontinuity, and the plasma on each side is effectively isolated from the plasma on the other. This is a sharper, more definitive boundary type than what the standard heliosphere models described. If the heliopause is closer to a tangential discontinuity than to a gradual mixing layer, the implications for cosmic ray transport for the exchange of material between the solar wind and the interstellar medium, and for the structure of the hydrogen wall outside the boundary, are all different from what the gradual mixing model predicted. There is a specific number embedded in the cosmic ray anomaly that is worth extracting. The change in galactic cosmic ray flux at the heliopause boundary occurred over a distance that the Voyager data constrains to less than a few AU. The mean free path for cosmic ray diffusion at the measured energies, calculated from standard scattering theory using the measured magnetic field strengths, should be 10 to 100 ARIU or more. The observed transition distance is at least 5 to 30 times smaller than the diffusion physics predicts. This factor of 5 to 30 discrepancy in the transition distance is independent of and additional to the factor of 40 discrepancy in the density. Two separate measurements. Two separate discrepancies, both pointing at the same conclusion. The standard physical description of the heliopause is missing something. The most honest summary of the state of knowledge is this. Before 2012, we had a model, The model predicted the structure and properties of the heliopause with enough success on the things that could be tested from inside that it had become the accepted description. In 2012, the first direct measurement from outside the heliopause showed that 3 independent properties of the boundary were significantly different from the model's description. The model is now known to be wrong in these 3 respects. Revised models are being constructed that attempt to explain all 3 anomalies simultaneously. No revised model has yet achieved a complete and broadly accepted explanation of all 3. The situation is the situation that defines the leading edge of a scientific field. The old model is known to be incomplete. The replacement is not yet agreed upon. And the data from the 2 Voyager probes represents nearly the entirety of direct observational constraints on the correct model. One way to understand why the 3 anomalies together are more significant than any single one is to consider what it would take to explain each one in isolation. The density anomaly alone could be explained by local interstellar medium structure, a denser region of the cloud near our heliopause. This explanation is physically plausible and probably captures some of the truth. The magnetic boundary sharpness alone could be explained by specific properties of the interstellar magnetic field in our vicinity, an orientational strength that creates a more effective barrier than the model assumed. This too is physically plausible. The cosmic ray step function alone could be explained by specific features of the interstellar magnetic field that create a more reflective boundary for cosmic rays than the model described. Also plausible, but explaining all 3 simultaneously with the same physical description of the heliopause and the surrounding medium is significantly harder. 3 independent anomalies constrain the solution space far more tightly than any single anomaly does. A correct model must explain all 3 simultaneously with a physically consistent description. No current model fully achieves this. The anomalies are not simply additive problems. They are multiply constraining. There is a historical parallel worth noting for what it means when 3 independent measurements disagree with a model. In the late 19th century, there were 3 independent anomalies in classical physics that the model could not explain. The photoelectric effect behaved in ways that wave optics could not account for. The spectrum of blackbody radiation diverged from classical prediction at high frequencies in a way called the ultraviolet catastrophe, and the perihelion precession of Mercury's orbit exceeded the Newtonian prediction by a measurable amount. Each anomaly could, in isolation, be attributed to some specific effect not yet incorporated into the model. All 3 together pointed at something more fundamental. Classical physics was incomplete, and a deeper framework was needed. That framework turned out to be quantum mechanics and general relativity. The 3 Voyager anomalies are not at the same scale of theoretical significance, but the structure is recognizable. 3 independent measurements from 3 independent instruments, all departing from the model in the same direction, pointing at a gap in the model's description of physical reality. The heliosheath crossing deserves one more specific detail. When Voyager 1 crossed the termination shock in December 2004, it entered a region that had never been directly sampled. The heliosheath is not observable from inside the inner heliosphere by any currently available instrument. Its properties were entirely modeled. What Voyager found as it moved through the heliosheath in the years between 2004 and 2012 was a plasma more complex and hotter than the models had described. The ions were being heated in the heliosheath by a mechanism the models underestimated. Pickup ions, neutral atoms from the interstellar medium that had drifted into the heliosphere and been ionized by the solar ultraviolet radiation, were being incorporated into the solar wind flow and carrying disproportionate energy. This pickup ion heating was not well represented in the pre-Voyager heliosheath models. It is one of the reasons the plasma temperatures in the heliosheath differed from predictions. Voyager 2's direct plasma measurements at its 2018 crossing confirmed anomalously high plasma temperatures in the heliosheath just inside the heliopause, adding to the evidence that the standard heliosheath model was underestimating the heating processes in the outer solar wind. What the 3 Voyager anomalies collectively describe is a heliopause that is physically more interesting than the standard model suggested. A gradual mixing layer would be a relatively passive boundary. A sharp, magnetically distinct, density anomalous membrane is a more active interface, one that mediates the exchange of material, energy, and cosmic rays between the heliosphere and the interstellar medium in ways that are not yet fully understood. Understanding this interface more completely is one of the central scientific motivations for the Interstellar Probe concept, not just to measure what is on the other side of the boundary, but to understand the boundary itself, its structure, its stability, and what physical processes maintain it against the tendency of the two plasmas to mix. The Voyager measurement showed the boundary is sharp. The Interstellar Probe would show why. We spent centuries studying the stars. We never properly studied the thing we were sitting in. Every observation of the universe in the history of human astronomy was made from inside the heliosphere. Every telescope, every radio dish, every satellite observatory, every signal ever captured from a distant galaxy passed through the heliosphere before reaching the detector. The heliosphere was always the medium. It was always present, and its external properties, what it looks like from outside, what the material surrounding it actually consists of, had never been directly measured until 2012. We were describing the universe through a lens we had never characterized from outside. The heliosphere does something that does not appear in ordinary descriptions of what makes Earth habitable. It shields the inner planets from the full galactic radiation environment. Galactic cosmic rays are high-energy particles, mostly protons, traveling at 99% of the speed of light or higher. They are produced by supernovae, by pulsars, by the jets of active galaxies, by any process in the galaxy energetic enough to accelerate matter to relativistic speeds. The galaxy is permeated by these particles moving in all directions at all times. The heliosphere filters them, partially, imperfectly, but measurably. Inside the heliosphere, the solar magnetic field deflects many lower-energy galactic cosmic rays, reducing their flux significantly relative to the interstellar background. The cosmic ray environment that life on Earth evolved in for 8 billion years was the cosmic ray environment as filtered by the heliosphere. The shielding was part of the physical conditions that shaped what living things became. It was not incidental, it was structural. The strength of that shielding depends on the heliosphere's size and structure. Its size depends on two forces, the solar wind pushing out and the interstellar medium pushing in. If the external pressure is 40 times higher than the models assumed, the heliosphere is more compressed than the models described. The shielding geometry is different. The radiation environment inside the heliosphere is different from what calculations built on the old model values would produce. How different? The modeling work required to translate the Voyager measurements into revised shielding estimates is ongoing. The precise answer is not yet available. The direction is unambiguous. The implications extend over geological time. The solar system has completed roughly 18 to 20 orbits of the Milky Way during its existence. Each orbit takes approximately 225 to 250 million years. During each orbit, the solar system passes through different regions of the galaxy, with different interstellar medium densities. The spiral arms, regions of enhanced gas and active star formation, have higher concentrations of interstellar material than the interarm regions. As the solar system passes through a spiral arm, the external pressure on the heliosphere increases, the bubble compresses, and the shielding against galactic cosmic rays decreases. Compress it enough, and the heliopause moves inside the orbit of the outer planets. Under those conditions, the galactic cosmic ray flux at Earth's surface would be significantly higher than it is today. Whether this correlates with events in the geological and biological record is an active research question. The correlations exist in some analyses. The consensus is not formed. The physics of a compressible heliosphere responding to varying external pressure is real regardless. The local bubble adds a specific dimension. The solar system entered this low-density cavity created by ancient supernovae within the past 1 to several million years. Before entering the bubble, when the solar system was in denser interstellar material, the heliosphere was more compressed. The cosmic ray environment at Earth was different. Life was evolving under it. The heliosphere's size and properties over biological time are not fixed. They vary with the sun's position in the galaxy. Here is the thing that you cannot unknow once you understand it. We are better acquainted with the properties of matter at the edge of the observable universe 46 billion light-years away. than we were with the properties of the gas within a few hundred AU of our own sun before 2012. We had measured the cosmic microwave background to extraordinary precision. We had imaged a black hole shadow 55 million light-years distant. We had detected gravitational waves from collisions billions of light-years away. And we had never directly measured the density of the material right outside our front door. The interstellar medium immediately outside the heliopause is too thin to produce detectable absorption features in nearby starlight, too close and too uniform to be mapped by large-scale surveys. Easier to see from far away than to characterize from inside. The only way to know what it actually is was to send something through. We sent something through. We sent something through, on 4 watts, with a 22-hour signal delay, and what came back was 40 times what the model predicted. The universe we have been describing for centuries was described from inside a structure whose external properties we had never measured. The description remains largely accurate in its broad architecture. But the calibration of the environment in which all our observations were made now has a new number attached to it, 40 times. That is the correction factor, applied to the medium we live inside. Here is a thought experiment worth sitting with. The year is 1950. You are an astronomer tasked with characterizing the interstellar medium immediately outside our solar system. You have no spacecraft, no instruments that can be sent to the outer solar system. You must work entirely from observations made from Earth or from early satellite platforms in Earth orbit. What do? You study the spectra of nearby stars. The light from those stars passes through the interstellar medium before reaching your telescope, and it picks up absorption features at specific wavelengths corresponding to the gas it passed through. You analyze those features to infer the density and composition of the intervening material. You study the polarization of starlight to infer the orientation of the local magnetic field. You measure the cosmic ray flux at Earth's surface and use the energy spectrum in arrival directions to infer properties of the medium those particles traveled through. You build theoretical models of how the solar wind should interact with this medium, calibrated against whatever solar wind measurements you can make at Earth's orbit. This is exactly what astronomers did over the following decades. The result was the standard model of the heliosphere that existed before 2012, and it predicted a plasma density outside the heliopause that was 40 times lower than what Voyager measured. There is a specific quality to this kind of discovery that is worth naming. Once you know the heliosphere's external properties were not what the models described, you cannot unknow it. Every measurement made before 2012 that assumed standard model properties for the heliosphere, every calculation of cosmic ray shielding, every model of the sun's influence on the local interstellar medium, every estimate of the radiation environment inside the heliosphere over geological time was built on an assumption about the external density that was 40 times off. Not every conclusion drawn from those calculations was wrong. Many were robust to the specific value of the external density, but some were not, and identifying which conclusions were sensitive to the external density assumption requires going back through decades of work with the correct value and checking. The solar system's orbit around the Milky Way takes approximately 225 to 250 million years per circuit. At some point in the last 30 to 40 million years, the solar system last entered the current interarm region, the relatively low-density space between the Perseus arm and the Sagittarius arm, which is where we currently reside. Before that, we were in denser spiral arm material. The transition from spiral arm to interarm involved a change in the external pressure on the heliosphere, which means a change in the heliosphere's size and shielding properties, which means a change in the cosmic ray environment reaching the inner solar system. The magnitude of the change depends on the actual external density in each region, which is one of many reasons the Voyager measurement matters. The 40 times correction factor on the local interstellar density affects how large those changes were in the past and will be in the future. There is something epistemically strange about the history of astronomy that the Voyager findings make legible. We are better acquainted with matter at cosmological distances than with matter in our own immediate galactic neighborhood. We know the cosmic microwave background to extraordinary precision. We know the expansion history of the universe back to fractions of a second after the Big Bang. We know the composition of stellar atmospheres thousands of light years away to better than 1%. and we did not know the electron density of the gas immediately outside our own solar system until a spacecraft that launched when the Carter administration was taking office sent a signal back 47 years later. The far is easier to observe because it is abundant and bright and produces signals that propagate across cosmic distances. The near but diffuse is hard to observe from inside because it is transparent to most wavelengths and produces no convenient bright signal to analyze. The only way to know it was to go there. The heliosphere's role as a cosmic ray shield over biological timescales is not a speculative connection, it is a quantitative one. The galactic cosmic ray flux inside the heliosphere is measurably lower than the interstellar background. The difference is energetically significant. At the DNA level, galactic cosmic rays capable of penetrating the heliosphere and Earth's atmosphere and magnetic field can cause ionization events in biological tissue that damage the molecule. Life's repair mechanisms have been selected over 8 billion years under the radiation environment as filtered by the heliosphere. Change the filter properties and the selection pressure changes. The standard model's description of the heliosphere shielding properties used the 40 times wrong external density as an input. The revised description, built from Voyager's measurement, produces different shielding properties. The radiation environment that shaped life over geological time was somewhat different from what the standard model described. How different depends on modeling work still in progress. The observation from inside problem has a specific structure worth making explicit. When astronomers observed the absorption features of starlight passing through the interstellar medium between our solar system and nearby stars, the light those features imprinted traveled through two distinct media before reaching the telescope. It traveled through the interstellar medium between the star and our heliopause. Then it traveled through the heliosheath and inner heliosphere before arriving at Earth. The properties of the interstellar medium were being inferred from data that had already been modified by the heliosphere. The heliosphere's filtering effects on the observed signals were accounted for using the standard model. If the standard model had the external density wrong by 40 times, the correction applied for the heliosphere's effects was wrong, and the inferred interstellar medium properties carry that error. Not all observations are sensitive to this at the level of the 40 times factor. Many astrophysical observations are robust to a factor of 40 change in a quantity that is already very small. But some observations are sensitive to it, and those need to be reviewed. The practical consequences of the density correction for future interstellar mission planning are direct. A spacecraft crossing the heliopause into a medium 40 times denser than the standard model predicted would experience different conditions than the pre-Voyager design assumptions described. The flux of interstellar dust grains, which scales with the medium density, will be higher. The bombardment rate on the spacecraft's surface from neutral interstellar atoms, which also scales with density, will be higher. The properties of the plasma the instruments will measure will be in the range Voyager found, not the range the models predicted. Any instrument designed before 2012 to detect interstellar plasma at the predicted density would be in the wrong measurement range. Instruments for future missions must be designed around the actual measured range. This is the direct operational legacy of the Voyager measurement. Every instrument for every future interstellar mission will be calibrated against 0.08 electrons per cubic centimeter rather than 0.02. There is a broader epistemological point embedded in the Voyager findings that applies beyond heliospheric science. It is about the limits of inference from inside a bounded system. We had built a detailed, internally consistent description of the heliosphere and its surrounding medium using observations made from inside the heliosphere. The description was internally consistent because all the observations were filtered by the same boundary whose properties we were trying to infer. The description was detailed because we had many observations spanning many decades, but a description built entirely from inside a boundary cannot fully determine the properties of the boundary from outside, for the same reason that you cannot determine the reflectivity of a mirror by observing only the reflected image, never the mirror itself from the outside. The 40 times discrepancy is what the inside view missed about the outside, and it took 47 years to get outside to look. The geological implications of the density correction have been explored in the scientific literature with appropriate caution. The solar system has been in the local bubble for roughly 1 to 3 million years. Before entering the bubble, when the external interstellar density was higher, the heliosphere would have been more compressed. A more compressed heliosphere means higher galactic cosmic ray flux at Earth. Higher galactic cosmic ray flux has been proposed as a contributor to increased cloud formation in Earth's atmosphere through ionization of atmospheric molecules. Increased cloud formation affects the Earth's energy balance and could contribute to cooling. Some analyses have found correlations between the solar system's galactic position, estimated cosmic ray flux, and the geological record of ice age cycles. These correlations are suggestive but not proven. The causation chain is long and each link has uncertainties. What the Voyager measurement adds is a direct constraint on the external density right now, which anchors the calculation for other positions and times in a way that the pre-Voyager estimates could not. The specific claim that we were observing the universe through an uncharacterized lens is not rhetorical, it is literal. Consider the measurement of the galactic cosmic ray spectrum at Earth. This spectrum is used to calibrate models of cosmic ray propagation through the interstellar medium. The spectrum measured at Earth is not the interstellar cosmic ray spectrum. It is the interstellar spectrum as modified by the heliosphere's filtering effects. Removing the heliosphere's modification to recover the true interstellar spectrum requires a model of the heliosphere's filtering properties. That model used the standard external density as an input. With a 40 times density correction, the external pressure on the heliosphere changes, the heliosphere's size and shape change, and the filtering model changes. The unfiltered interstellar cosmic ray spectrum inferred from Earth-based measurements using the revised heliosphere model will differ from the spectrum inferred using the pre-Voyager model. This is a real, quantitative correction that propagates into cosmic ray astrophysics, far removed from heliospheric physics. The implications for the search for life beyond our solar system, while indirect, are worth noting. The habitability of planets orbiting other stars depends in part on the cosmic ray environment those planets experience. A star with a strong stellar wind and a large astrosphere around it shields its planets from galactic cosmic rays more effectively than a star with a weaker wind and a smaller astrosphere. The properties of stellar astrospheres are inferred from models analogous to the heliosphere models that Voyager found to be significantly off. If our own heliosphere model was 40 times wrong about the external density, models of other stars' astrospheres built on similar assumptions may carry similar systematic errors. The habitable zone concept, already complex enough when accounting for orbital position and stellar luminosity, becomes more complex still when the cosmic ray shielding properties of the stellar wind are factored in, using models we now know are inadequately constrained. Every future mission to interstellar space will carry a measurement Voyager bled out 47 years to give us. The Interstellar Probe concept has been in NASA's formal mission planning process for years. It is not a speculative proposal. It is a mission concept that appeared in the Heliophysics Decadal Survey, the process through which the scientific community formally establishes priorities for future investment. The justification is direct. Voyager showed that the interstellar medium just outside our heliosphere differs dramatically from everything the models predicted. A dedicated mission with modern instruments designed around the actual anomalies Voyager found rather than the model expectations is the logical next step. The target is 1000 AU within 50 years of launch. Voyager 1 is at roughly 165 AU today, growing at 3.6 AU per year. At that speed, 1000 AU would take about 300 years. The Interstellar Probe would need to travel at approximately 20 AU per year, 6 times faster. Conventional launch trajectories cannot achieve this. The leading concept is the solar Oberth maneuver. The Oberth effect describes how rocket burns produce more useful kinetic energy when performed at higher speeds. A spacecraft that falls toward the Sun from the outer solar system reaches maximum velocity at its closest approach. Fire the engine at that exact moment and the energy gain is amplified by the Sun's gravity in ways impossible at larger distances, close enough to the Sun, and the departure velocity becomes sufficient to reach 1000 AU in 50 years. The thermal challenge is serious. The Parker Solar Probe, approaching within about 4 million miles of the Sun's surface, requires a heat shield capable of withstanding temperatures above 1400 degrees Celsius. The Interstellar Probe's solar Oberth maneuver would require a closer approach. The engineering does not currently exist in a form compatible with protecting a full instrument payload. The physics is sound. The hardware needs development. This is why the mission is a concept under study, not a spacecraft under construction. What the mission would carry that Voyager does not have was shaped directly by what Voyager found: a modern plasma analyzer, direct measurement of ion species, temperatures, and flow velocities. The measurement Voyager 1's failed plasma instrument would have provided at the 2012 crossing. A dust detector. Interstellar dust grains carry compositional information Voyager has no ability to gather. A Lyman alpha ultraviolet imager to photograph the heliosphere from outside, providing the first external image of the shape of the bubble the Sun carves into the interstellar medium. That last instrument is worth sitting with. The heliosphere has never been photographed from outside. We have models of its shape. We have 2 crossing data points and remote sensing from inside. We have never seen it. An interstellar probe positioned outside the heliopause could turn back and photograph the entire structure. The first image of what we live inside, from the outside. Voyager 2 crossed the heliopause on November 5, 2018, at roughly 119 ASU from the Sun. 2 ASU closer than Voyager 1's crossing at 121 ASU. A different direction. A different heliographic latitude. The crossing distance difference directly confirms the heliosphere's asymmetry between the nose and the flanks. Because Voyager 2's plasma science instrument is still functioning, it provided something Voyager 1 could not give. Direct plasma measurements at the crossing. The data confirmed elevated external density, consistent with Voyager 1's findings. It also revealed anomalous plasma temperatures in the heliosheath significantly higher than the models predicted. A third anomaly CAS, distinct from density and boundary sharpness, pointing in the same direction. The outer heliosphere is physically different from what the models described. 2 probes, 2 crossings, both finding anomalies of the same general character. This is not a single data point. It is a pattern that persists across independent measurements in 2 different directions, 6 years apart. The standard model is missing something structural about the heliopause. What that missing thing is remains an open problem. The data from Voyager has defined the problem precisely. Resolving it requires more data points, more crossings, more instruments at the boundary. The Interstellar Probe would add 1. Future missions would add more. The full characterization of the heliopause is the work of decades and multiple missions. Voyager 1 is still transmitting. The signal arrives 22 hours after each measurement. The instruments are expected to operate until roughly 2025 to 2030, after which the declining RTG output will no longer support the science payload. When the last instrument goes dark, the spacecraft will continue moving through interstellar space on accumulated momentum at 38,000 miles per hour. Silent, in a plasma 40 times denser than the models predicted when it launched. In approximately 40,000 years, it will pass within about 1.6 light-years of a small red dwarf in the constellation Camelopardalis. The star's gravity will barely deflect the trajectory. Voyager will continue. The gold-plated record it carries, with greetings and music from Earth, will keep moving through a medium nobody correctly predicted indefinitely. The measurement Voyager bled 47 years to deliver is already built into every instrument choice for every interstellar mission currently being designed. The anomalies Voyager returned are the hypotheses the next mission will test. Without the 22-hour signal and the 40 times density, there would be no hypotheses worth testing. The probe that flies in 20 or 30 or 50 years will know what Voyager discovered. Every design decision will be calibrated against the reality Voyager measured, not the model that preceded it. The Lyman alpha imager concept deserves specific attention for what it would reveal. The heliosphere is surrounded on the outside by a region of neutral hydrogen atoms that pile up outside the heliopause, slowed by their interaction with the boundary. This region, called the hydrogen wall, absorbs ultraviolet light at the specific Lyman alpha wavelength of 121, 6 nanometers. From inside the heliosphere, the hydrogen wall creates a measurable dimming of Lyman alpha photons from distant stars observed through it. This effect has been detected from inside and used to infer some properties of the hydrogen wall. But an imager placed outside the heliopause, looking back at the entire structure, would see the hydrogen wall as a faint ultraviolet glow surrounding the heliosphere in 3 dimensions. The shape, extent, and asymmetry of that glow would map the shape of the boundary directly. This would be the first direct external image of the structure we live inside, the heliosphere in its actual form, visible for the first time. Voyager 2's plasma science instrument, which has been operating continuously since 1977, unlike Voyager 1's which failed in 1980, provided a measurement at the heliopause crossing that no model had anticipated: the temperature of the plasma in the heliosheath, the region just inside the heliopause, was significantly higher than the standard models had predicted. Not slightly elevated, significantly elevated. Significantly elevated. The thermal energy of the particles in the outer heliosheath did not match the expected energy distribution. This anomaly is distinct from the density anomaly found by Voyager 1 and the boundary sharpness anomalies found by both probes. It represents a third category of departure from the models, and like the others, it points in the same direction. The outer heliosphere and its boundary region are physically different from what the standard models described. Two crossing data points in two directions is not enough to characterize a three-dimensional, asymmetric, dynamic boundary. Voyager 1 crossed near the nose of the heliosphere, the compressed leading edge. Voyager 2 crossed on the flank, closer to the equatorial plane. The tail of the heliosphere, the region behind the Sun in its direction of travel, may extend hundreds of AU further than the nose. No spacecraft has approached the tail. We have no data from the tail crossing. The heliosphere's shape in the tail direction is inferred from models, and the models now have a 40 times density correction that changes their output. The full characterization of the heliopause requires crossings at multiple positions around the three-dimensional boundary. Voyager provided 2. A future mission would provide more. The Interstellar Probe's value was not just in the data it would return, but in the sampling geometry it would provide. The Interstellar Probe, if built and flown, would operate in a fundamentally different environment than Voyager. It would know before launch that the external density is approximately 0.08 electrons per cubic centimeter. Its instruments would be calibrated for that value, not for 0.2. Its data would be measured against revised models that incorporate the Voyager corrections. The science it returns would be building on Voyager's foundation rather than on the pre-Voyager model. This is how science advances. Each generation of measurement defines the parameters for the next generation. Voyager defined the parameters for interstellar science by being wrong enough to be interesting. Everything that follows will be calibrated against what Voyager found after the last science instrument goes dark, probably between 2025 and 2030. Voyager 1 will continue moving through interstellar space on its accumulated momentum. No engine, no power, no signal. Just mass moving at 38,000 miles per hour in a direction it was aimed in 1980. In 40,000 years, it will pass within approximately 1/6 light-years of a small red dwarf star called AC plus 793888 in the constellation Camelopardalis. This star is currently not visible to the naked eye. By the time Voyager passes near it, the star's proper motion across the sky will have changed its position significantly from where it appears today. Voyager will not stop. The star's gravity will barely deflect the trajectory. The probe will continue. In hundreds of millions of years, its trajectory through the galaxy becomes impossible to predict because the gravitational influences of countless stars will gradually perturb it. What can be said is that it will keep moving, silently, carrying a gold record pressed with greetings from a civilization that existed briefly enough on geological timescales that the probe was launched and the civilization was gone, before the probe reached a single other star. The Interstellar Probe appeared in the 2024-2030 Heliophysics Decadal Survey as a priority medium-class mission. The Decadal Survey process is the formal mechanism through which the scientific community, through a National Academy of Sciences panel, evaluates and ranks proposed missions based on their scientific merit and feasibility. Appearing in the Decadal Survey does not guarantee funding, but it is the community's formal statement that the mission is scientifically compelling and should receive serious consideration. The inclusion of the Interstellar Probe in the Decadal Survey represents the heliophysics community's collective judgment that the Voyager anomalies are important enough to dedicate a dedicated mission to following up. This is not a peripheral interest. This is the field's assessment of its highest priority open question. The sample size problem is the central limitation of what Voyager can tell us about the heliosphere and the interstellar medium. 2 spacecraft, 2 crossings, 2 directions out of the full 3-dimensional boundary. The heliopause is a closed surface surrounding the entire heliosphere. It has a nose direction, 2 flank directions, a polar direction above the ecliptic plane, a polar direction below, and a tail direction stretching back behind the Sun's motion. Voyager 1 sampled 1 point near the nose. Voyager 2 sampled 1 point on the northern flank near the equatorial plane. The tail is entirely unsampled. The southern polar region is entirely unsampled. The second flank is entirely unsampled. The second flank is entirely unsampled. The heliopause's properties at those unsampled locations are inferred from models, and those models now have a known 40 times density correction applied to an external boundary condition that was previously wrong by that factor. The tail crossing, in particular, is scientifically interesting because the tail is where the solar wind material piles up furthest from the Sun, and where the structure is most likely to differ from the nose. No mission currently in development will reach the tail in any reasonable timeframe. What 1000 AU enables that 165 AU cannot is a survey of the transition from the near heliopause interstellar medium to the truly undisturbed local interstellar medium to the truly undisturbed local interstellar medium. The heliosphere does not simply stop at the heliopause, it disturbs the medium for some distance beyond the boundary. The hydrogen wall, the region of piled up neutral hydrogen just outside the heliopause, extends for tens of AU beyond the boundary. The disturbance of the interstellar magnetic field by the heliosphere, the draping of field lines around the outer boundary, extends further still. To reach undisturbed interstellar medium, you need to travel far enough from the heliopause that the heliosphere's influence is negligible. How far that is depends on the properties of the medium and the heliosphere's interaction with it, which Voyager's measurements have constrained but not fully determined. An interstellar probe at 1000 AU would be roughly 800 AU past the heliopause, far enough that the heliospheric disturbance of the medium should be small compared to the medium's natural variation. At that distance, direct measurements of the undisturbed local interstellar medium become possible. Those measurements are the ground truth against which all the model predictions, revised with Voyager's corrections, can be tested. The duration of Voyager's science return, even from beyond the heliopause, is likely to be measured in years more than decades. The RTG power output continues to decline by approximately 4 watts per year. Science instruments will be shut down sequentially to maintain power for the most critical measurements. The magnetometer, one of the lowest power instruments, may be among the last to operate. The plasma wave instrument, which requires somewhat more power but provides unique measurements, may be shut down before the magnetometer. The exact sequence will depend on the actual power trajectory and the team's scientific priorities. What seems clear is that the window for interstellar science from Voyager is limited and shrinking. Every year of remaining operation is a year of additional data from inside the interstellar medium that no future mission will duplicate for decades. The measurement cadence of the instruments, optimized over 47 years of operations to balance science return against power budget, continues to evolve as the power budget tightens. The legacy of the Voyager mission is sometimes described in terms of the spacecraft itself, the engineering, the longevity, the distances covered. This is accurate, but misses the more important legacy, which is scientific. Voyager changed what questions it is possible to ask about the heliosphere and the local interstellar medium. Before 2012, the question was, how well do our models describe the heliopause? The answer, assumed to be, reasonably well. After 2012, the question became, what is actually at the heliopause, and why does it differ from what we modeled? That is a fundamentally different question, more specific, more constrained by data, more productive of testable hypotheses. The Interstellar Probe will be designed to answer the second question, not the first. The mission design is shaped by Voyager's findings in every detail. Without Voyager's anomalies, there would be no well-defined second question to ask. There is something in the 22-hour signal that deserves one final observation before we leave this section. The signal delay is usually discussed as an obstacle, a limitation on the science Voyager can do and the operations team can manage. it is also something else. It is a physical demonstration of the scale of the task. Every day, a signal arrives that left Voyager 22 hours ago. That 22-hour duration is the light travel time across 22 light hours of space. It is an interval you can feel. You can wait 22 hours. You know approximately what 22 hours feels like as an experience duration. And the distance that corresponds to that duration, the 11 billion miles between Earth and Voyager, is the scale of the measurement we are making. The 22-hour signal is not just a delay, it is a clock ticking out the size of the measurement. Each time it arrives, it says, "This far." Still transmitting. Still in the medium. Still measuring. The horizon turned out to be in the wrong place. This is where we began. It is the only honest place to return. The ship crossed. The engineering worked for 47 years in conditions no instrument was designed to survive. The spacecraft that was supposed to study Jupiter and Saturn is now the only human-made object in interstellar space, transmitting measurements from a medium that no model correctly predicted on a 22-hour signal running on 4 watts. 40 times, 3 instruments, 3 independent physical phenomena. The plasma density, 40 times above the predicted value. The magnetic boundary, sharper than any model described. The cosmic ray transition, a step function, where the models expected a gradual ramp. 3 separate physical measurements, each departing from the model, all pointing in the same direction. The heliopause is harder, more defined, and more physically distinct than 50 years of theoretical work had described. The material on the other side is denser than anything the inside view predicted. The heliosphere is not a gradual fade, it is a wall. Inside, solar wind, solar field. The direct physical presence of our star. Outside, a plasma 40 times denser than expected. A magnetic field pointing elsewhere. A cosmic ray flux that steps from one level to another at the boundary. 2 physically distinct regimes, separated by a boundary far more definite than the diagram showed. We lived inside this structure for the entire history of life on Earth. We described the universe through it for the entire history of astronomy. We never looked at it from outside until 2012, when a spacecraft running on a nightlight in a plasma nobody predicted sent back a 22-hour signal that changed the description of the room. The signal is not a metaphor for human ambition. It is not a symbol of ambition. It is a measurement, a plasma density, a magnetic field direction, a cosmic ray flux value. These facts are what matter. Voyager is the instrument that delivered them. The instrument is secondary. The facts are what stay. If tonight gave you something, a subscribe helps this channel find more people who need this kind of quiet. The horizon was in the wrong place. The ship crossed it anyway. The signal is still coming. There is a specific quality to what the 22-hour signal has been delivering that only becomes legible at the end of this story. At the start, the signal was the distance, a measure of how far the probe was. 22 hours is a long time for a signal to travel. It established the scale of what Voyager had done. By the end, the signal is something different. It is a daily arrival from a medium that no model correctly predicted, carrying measurements that required revising 50 years of theoretical work. The distance has not changed. The signal delay has not changed. But what the signal means has changed completely. That is the transformation the central specimen undergoes in a script that works correctly. The signal at the beginning is a measure of reach. The signal at the end is a measure of discovery. The 22 hours that felt like a limitation at the start is now a clock counting out the size of something that surprised us. The 3 anomalies Voyager returned are not the end of the story about the heliosphere. They are the beginning of a more accurate version of it. Every revised model being built to explain the sharp heliopause, the 40 times density, and the step function cosmic ray transition will make a new set of predictions. Those predictions can be tested by an interstellar probe with modern instruments. The testing will reveal whether the revised models are right. If they are right, we will have a description of the heliopause that matches direct measurements from 3 crossings in 3 directions. If they are wrong, we will have 3 crossings in 3 directions, all disagreeing with the revised model, and the science will have a new and better constrained problem to solve. Either outcome advances the description of physical reality. This is not a failed model being replaced. This is SIS working through the iterations that eventually produce accurate descriptions of the world.